Hello everyone, welcome to today's lecture. What we discussed last time was introduction of ruthenium tetroxide as a aggressive oxidizing agent for the conversion of alcohols to the corresponding acids, cleavage of the CC bond to the corresponding dialdehyde or diketone or dicarboxylic acids depending on the condition. Also we saw that the olefins can be converted to the corresponding epoxide if one uses a nitrogen ligand, and we have also seen that how catalytic amount of ruthenium reagent such as ruthenium dioxide or ruthenium trichloride is used in conjunction with a co-oxidant such as sodium metaperiodate for preparing the ruthenium tetroxide in the reaction medium, and thus only catalytic amount of the ruthenium salts can be utilized for this CC bond cleavage. Now towards the end of the last class that we saw that ethers or acyclic ethers or cyclic ethers can be converted to the corresponding esters or lactones, and that was mainly because, as we had discussed earlier, that since the ruthenium tetroxide is a very strong oxidizing agent, is a very aggressive oxidizing agent, it reacts with solvents such as ethers or pyridine or even benzene. That was the reason why the oxidation of the acyclic ethers to the esters or cyclic ethers to the lactones took place. So we now will see in today's class the mechanism of how does that oxidation occur. For example, we can start with the cyclic ether such as tetrahydrofuran. This tetrahydrofuran then reacts with the ruthenium tetroxide and forms a species of this kind where there is a positive charge on the oxygen and of course there is a negatively charged ruthenium species which is attached to the oxygen. Now what can happen is this negatively charged part of the ruthenium species is able to take the proton from here, and then in the process it breaks this in this fashion to form an oxonium ion and another ruthenium species of this type. Now this ruthenium species can go and react with the oxonium ion at the carbon which is electrophilic to form this species, and this species then undergoes oxidation to form this type of lactone and a ruthenium species. This ruthenium species loses water to form ruthenium dioxide. So ruthenium tetroxide has got converted to ruthenium dioxide, and in the process ether which is tetrahydrofuran has got converted to the corresponding lactone. This is how the reaction occurs, and it is a very useful reaction. As we had seen different types of examples, I can show once again. Those examples are here. For example, you have this substrate of this kind going to the corresponding lactone, and of this type to the corresponding lactone. Therefore, this is a very useful conversion of ethers to the corresponding oxidized esters or lactones, depending on whether it is acyclic or cyclic ether. Now, there is a modification of the ruthenium tetroxide. We saw in many cases that the aldehyde is oxidized to the corresponding acid. That means if you allow a primary alcohol to react with ruthenium tetroxide, it forms the corresponding acid, and I had already discussed the mechanism of the formation of the acid from aldehyde using ruthenium tetroxide. But many a times when such conversions are required to be stopped at the aldehyde stage, then there is a problem, and this becomes more important when say you carry out oxidative cleavage of a cyclic olefin or even an acyclic olefin, but with substrates which can give the corresponding aldehyde, but then these aldehydes are oxidized to the corresponding acid. So, basically what it means that we need to develop protocols which can allow the reaction to be stopped at the dialdehyde stage, because as I showed one example that C-C bond cleavage does not occur with reagents such as ozone or KMnO4 or such reagents, then ruthenium tetroxide becomes a better oxidizing agent to cleave that. But if such a cleavage does not allow to stop the reaction at the aldehyde stage, and if one wants aldehyde, then you unnecessarily go to the acid stage. Keeping these kinds of requirements in mind, Steve Ley in 1994 reported introduction of a reagent which is Tetra-n-propylammonium perruthenate, which is also popularly called as TPAP. In this reagent system, the good point is that it is having a large counter cation here, and that is useful because it can allow the solvent to be used which are normal organic solvents. In this reagent system, a co-oxidant which is also soluble in organic solvents can be used, and mostly it is the NMO, that is N-methyl morpholine oxide. This is N-methyl morpholine oxide, but also one can use sodium hypochlorite or oxygen as a co-oxidant. It is obviously very selective reagent and mild reagent compared to ruthenium tetroxide because of the large counter ion that is present. At the same time, it is a negatively charged ruthenium perruthenate species, and therefore it is having less reactivity compared to the ruthenium tetroxide. So, using this the alcohols can be converted to the corresponding aldehydes with no over oxidation or no reaction with multiple bonds. In this case, it was found that if molecular sieves are used, which are nothing but aluminosilicates, as they absorb water, to remove water, high turnover of the catalyst is possible. Now, of course, with the same reagent system, there are conditions under which primary alcohols can be converted to the corresponding carboxylic acids, but then that is not so much really required, but if one wants to see, this is the reference that you can check it. Now, with what is the mechanism of the TPAP based oxidation? It is very similar to the ruthenium tetroxide based oxidation, but here I have shown that the TPAP which is present here has this counter cation, which is large Tetra-n-propylammonium salt ammonium species that reacts with the alcohol to form this kind of species where the lone pair of electron on the alcohol reacts with the ruthenium with the movement of the electron density onto the oxygen, forming this intermediate, and this intermediate then can take up the proton, allows the oxidation to take place in this fashion, and one can generate the corresponding ketone and the ruthenium species, which is low valent compared to the starting ruthenium, which is ruthenium 7. The ruthenium 7 goes to ruthenium 5 here, 5, and this is then reoxidized with N-methyl morpholine N oxide to the TPAP, and one loses the corresponding N-methyl morpholine as a byproduct from the N-methyl morpholine oxide. So, this is the mechanism which is proposed for the oxidation of alcohols to the corresponding ketones. Obviously, this does not react further with the aldehydes to form the acid. So, examples are here, this kind of alcohol having a double bond is converted to the corresponding aldehyde with 85% yield. This kind of substrate having an epoxy alcohol and 2 double bonds, and of course the phenyl rings here which can be oxidized, and this substrate when it was reacted with a Swayam oxidizing agent, it gave only 12% of the oxidized product. On the other hand, with TPAP 78% of the corresponding aldehyde was formed. One can also see another example. Of course, in this particular case also the nitrogen has been protected as a CBZ group. CBZ group is nothing but COO benzyl group, CH2 phenyl. This is the protecting group for the, and this is what is called CBZ. And therefore, this is protected, and that gives the corresponding aldehyde, no over oxidation, no oxidation of the double bond. And another example is of course this lower one, where this protecting group is also unaffected, which is tertiary butyl diphenyl silyl. That is, this protecting group is like this. We have 2 phenyl rings here and tertiary butyl. So, this is OTBDPS, tertiary butyl diphenyl silyl. So, these kinds of different protecting groups are unaffected, and the reagent allows oxidation in a selective and mild fashion, and therefore it has become a very popular oxidizing agent. So, as I said that different protecting groups such as SEM, which is 2-trimethyl silyl ethoxymethyl like this, MOM, which is nothing but CH2O methoxymethyl protecting group for the alcohol or any alcohol type, or MEM, which is methoxy methyl ether. So, you have CH2 CH2O CH3. Then trityl group, which is nothing but this type of substrate from the oxygen here of course. Then you have a silyl group, benzyl group, paramethoxybenzyl group, tetrahydropyranyl group, acetate and benzoate protections. Also functional groups such as enones, double bonds, epoxides, halides, ethers are stable under the reaction conditions. So, therefore, TPAP is a very useful alternative for converting primary alcohols to the corresponding aldehydes or without cleaving various kinds of double bonds or tolerating different types of functional groups. It is also found that one can introduce a this type of solid phase catalyst where you have the part of the nitrogen is attached to say polystyrene based group, and such an oxidizing agent also is useful because you can recover and reuse it. Simply filter it off and the solid phase ruthenium reagent can be reused for the oxidation of alcohols to the corresponding aldehydes. So, this is what it was related to the ruthenium tetroxide based oxidizing agents, which were conveniently made useful for various transformations, and of course introduction of the TPAP as for mild and selective oxidizing agent. Now we go to another oxidizing agent, oxidation rather, and that is called as Tamao-Fleming oxidation. In the Tamao-Fleming oxidation, what is used is a carbon silicon bond of this type is converted to the corresponding carbon oxygen bond. That means this bond here is basically converted to the corresponding oxygen. This was introduced by Tamao, where he used a slightly different types of silicon based substrates and slightly different conditions, as one can see here with potassium fluoride, hydrogen peroxide, potassium bicarbonate in methanol. At the same time, Fleming introduced a somewhat robust silicon based substrate where there are only carbons which are attached on the silicon, carbon based groups which are attached, and this in the presence of potassium bromide, peracetic acid in acetic acid medium allows the conversion of this type of substrate to the corresponding alcohol. What it does it is clearly one can see that it allows the silyl group to be used as a masked OH group. Interestingly, what is very important in this oxidation is whatever is the stereochemistry of the original silicon substrate. That means if this substrate which is used has this type of silicon group attached, where the absolute stereochemistry is like this or like this. So, if one starts with this type of absolute stereochemistry, the hydroxy group also is coming from the same side. So if one takes this substrate, then one can get the corresponding alcohol which would look like this. So enantioselective hydrosilylation of alkenes followed by Fleming Tamao-Kumada. Of course, Tamao and Kumada did together the oxidation, so this is called as Tamao-Kumada oxidation, but popularly it is also called as Tamao-Fleming oxidation, can lead to the chiral alcohols. That means if one starts with any olefin like this, where there are two different substrates attached, or say for example something like this, and if one converts into the silyl group which is present here in this fashion, where you have now an asymmetric center that is being created, and if this is a chiral compound, then of course you can get the, upon this oxidation, the corresponding alcohol in a chiral fashion. So you start with a chiral substrate and you can get the corresponding chiral alcohol, because the oxidation that occurs is highly stereo specific or stereo selective reaction. Now in Tamao oxidation, one ligand on silicon must be hydrogen or a heteroatom, that is the condition. But in Fleming oxidation, all ligands on silicon are carbons. So there is a slight difference in the condition, reaction conditions, and therefore the requirements are slightly different. What is the mechanism of the Fleming oxidation? The Fleming oxidation essentially involves, as we saw, that a conversion of a stable silicon containing starchy material to a reactive silicon intermediate for further oxidation. So under the protic conditions, which was the initial condition that was reported by Fleming, it basically involved a regioselective protonation of the phenyl ring favoring beta silicon effect. That means this particular phenyl ring undergoes protonation in such a fashion that the proton gets attached to this particular carbon atom, and the positive charge is formed at the next carbon atom, which is the beta carbon atom. And this is because of the favoring beta silicon effect, which is nothing but a silicon hyperconjugation. It has stabilizing influence of a silicon atom on the development of a positive charge at a carbon atom one position away, that is a beta position, from the silicon. This is the alpha position and this is the beta position. So this particular formation of a positive charge at the beta carbon then eventually allows a proto-decylylation, because the negative charge that has come on the X, that is a, say for example if we use HBr, then it is a bromide ion. That bromide ion then interacts with the silicon, and this carbon silicon bond is broken to regenerate the aromatic system here, like benzene here, and in the process we generate the reactive silicon intermediate. So essentially this is nothing but a regioselective proto-decylylation to form a reactive silicon intermediate for further oxidation. This is the basis of the Fleming oxidation. Now in principle one can use any electrophile in place of H plus and carry out the cleavage of the carbon silicon bond and generate the corresponding aromatic compound. For example, we could also use a source of bromonium ion. That means a phenyl group could also be activated via bromination using either excess of bromine, which will of course give a source of Br plus as well as Br minus, or a bromide ion under oxidation condition that leads to the formation of a bromonium ion eventually for aromatic system to react with that electrophilic species, and in the case of bromine, then of course we get bromobenzene as a byproduct, and of course the same silicon, which is a reactive silicon intermediate for further oxidation, will form. Now this is the substrate that we have got that reacts with peracetic acid, where the peracetic acid replaces the X from here, HX is out, and we can get an intermediate of this type, which undergoes. Now this is the chiral center that we are talking about it. This is the chiral center that we are talking, the asymmetric center. Now this substrate looks very similar to a substrate that can be seen as equivalent to undergoing as Baeyer-Villiger oxidation, and in the Baeyer-Villiger oxidation also, if you recall, that the chiral center does not lose the chirality, and therefore this migration from here leaving the acetate ion out gives this intermediate. Now here the chirality is not lost, which now then reacts with another mole of peracetic acid, where peracetic acid attaches to the silicon here, forming this intermediate, and the remaining R primes which are present, which are the carbon substrates, they undergo Baeyer-Villiger type of oxidation similar to the one that I have shown it here, undergo to form with the first R prime you get the transfer like this here to give the substrate, which is again attacked by the peracetic acid to eventually give via Baeyer-Villiger oxidation the 2 OR primes here. So we have one OR substrate, which is what is derived from the alcohol, and then 2 OR primes from the silicon substituents, and then the acetic acid attacks onto this silicon substrate, and we get this particular product as the stable, ultimately stable silicon substrate, which upon basic workup like sodium hydroxide followed by protonation releases the alcohol and the silicon side product. So this is the Fleming oxidation, in which in 2 steps, first the silicon substrate which has 1 phenyl ring and 2 carbon substrates, 2 carbon based groups, undergoes proto-decylylation to form silicon X bond, and then with peracetic acid eventually one gets this alcohol which is having same chirality as the starting silicon substrate. So we will stop it at this stage today, and we will take it up in the next class, the other aspects of this Fleming-Tamao oxidation and their utility in organic synthesis. So you can go through some of the references I have mentioned already, you can go through those references as well as revise what I have discussed today. Till then, bye and thank you, and we will see you in the next class.